for this really nice, interesting talk. And we are ready to move to the next speaker. And next speaker is Stefano Marin from University of Michigan. Stefano, can you hear me?
Yes, I can hear you. And I just got a message that my internet might not be super good right now, but I hope everybody can hear me right now.
We can still hear you. I do hear that it's a little bit garbled, and I never know whether that's on my side or your side. But
it might also be because I'm nervous, so I might be talking up there.
No, that's not good. We'll blame it.
I'll share.
Okay. So when you're ready, please share.
Yeah, and maybe so. Okay, I'll just go ahead.
The title of the talk is the gamma ray emission correlations following spontaneous fission. So Stefano, please, when you're ready.
Right. Thank you very much, Dr. Jovanovic. So as he said, my name is Stefano Marin. I'm a third year now, PhD candidate at the University of Michigan, working with Professor Sarah Pozzi. And this is the second talk out of 5 today about the fission correlations. And I'm going to be focusing on gamma ray emission today. It's going to be more of a theory talk, more a simulation talk, because we haven't been to the lab too much recently, as I think most of the people here. So the motivation for this work is that special nuclear material undergoes spontaneous and induced nuclear fission. And after fission, the 2 fragments that are released start emitting neutrons at first, followed by photons. And these particles are very penetrating. Neutrons and gamma rays are, of course, uncharged. And therefore, we can detect them with technology, like with current day technologies. In this talk specifically, I'm going to be focusing on the gamma ray correlations in Californium-252. I'm going to mention a few times the Newton emission just to help in analysis of the gamma ray correlation, but today's topic is mostly focused on this. The mission relevance for this, for studying fission, as I said, is for non-proliferation applications. The signatures of neutrons and photons emitted by the source can be leveraged to characterize the sources. However, the signatures at emission can be quite complicated, and there is a lot of complex structure that intertwines the energy, the angles, the multiplicity together. So if we want to understand how we would detect these signatures at the detection, we have to use Monte Carlo simulations and evaluated nuclear data. However, nuclear data right now does not encompass all the predicted correlations that we know should appear in fission correlations and fission emission, and therefore we rely on, to a large extent, on physics-based fission event generators. I mentioned two of the ones that we use. The first one is the Lawrence Livermore and Lawrence Berkeley National Lab developed FRIA, as well as the Los Alamos developed CGMF. On the right, I show a figure that is kind of like a goal that we can think about of when we develop these codes well enough, when we understand the physics well enough, we should be able to reproduce data of this type. This plot here shows a spectroscopic measurement of a fission source using high resolution gamma ray detectors, inorganic gamma ray detectors. And as you can see, the structure is typical of a gamma ray band transitions for the highly rotating fission fragments. What we hope to do is to improve the models used in the fission event generators to the level where the angular momentum and the energy is treated to the point where this type of correlations can be predicted. So when I talk about observables in gamma ray emission, I usually talk about 2 things. We refer to 2 properties. We talk about the spectra of gamma rays as well as the multiplicity. To a lesser extent, we can also talk about the angular correlations of gamma rays, but this has been shown to be almost isotropic in the lab frame. On the top plot, I show a comparison between the CGMF code shown in the blue line compared to the experimental data shown in red. As you can see, the model-based calculation agree pretty well with the gamma ray emission spectra for high energies above about 1 MeV. However, the gamma ray energy there is some disagreement below 1 MeV in the lower energy portion of the spectrum. And this is not only for CGMF, but this applies in general to most model calculations, where getting the lower energy portion of the spectrum is harder. The second plot on the bottom shows the multiplicity distribution of gamma rays in fission. This is the event by event multiplicity distribution. And again, we can see that the comparison between model-based calculation, CGMF and FRIA, is in a slight disagreement with the evaluated data shown here and labeled by Polimi as the Valentine 2001 evaluation of this data. What is interesting to note is that they are different in different ways. So the two model-based calculation have two different relative widths. So the Freya calculation seems to be less sub-Poisson, and so very, very narrow for its mean, and the CGMF calculation seems to be too wide for its mean. So there is definitely a lot of room for improvement for the accuracy of these observables from gamma ray emission. And in order to do that, in order to go to the codes and try to improve the accuracy, we have to start talking the same language of the codes. We have to start looking at the fission fragments, because that's the central simulated subject of the fission event generators. One way to visualize how a fragment emits, gamma rays and neutrons is to look at the figure on the right. This figure is an internal excitation energy, intrinsic excitation energy, and angular momentum plot, where each point on this figure represents an initial or a combination of these two properties that a fragment might have at any given point. The ellipse in the top right shows the initial distribution that a fragment might be found in immediately after fission. And as you can see, there are two ellipses, one flat showing the uncorrelated hypothesis between excitation energy and angular momentum, and one showing a strong angle. This is, of course, this is still hypothetical. There is no strong basis for this strong correlation. And this is actually going to be one of the main topics for the next few slides. As you can see, a fragment that is created with a certain excitation energy above the separation, neutron separation energy, will emit neutrons until energetically possible. As soon as the fragment energy, the intrinsic excitation energy of the fragment, crosses below the neutron separation energy, shown here with the dashed line, the intrinsic excitation energy will be dissipated through statistical gamma rays. Statistical gamma rays in this case are very high energy, low angular momentum gamma ray emission. After reaching the ERAS band, which defines the coldest possible and lowest energy state a fragment can be found in given a certain value of angular momentum, the only choice for the fragment to reach its ground state is by emission of low energy, high angular momentum gamma rays. In this case, we can see that again, what complicates the analysis and the modeling of gamma rays with respect to neutrons is that there are actually multiple sources of gamma rays, whereas in Newton, there is only one source of evaporation. In trying to fix the secondary gamma rays, like the one emitted after the ERAS band is reached, we might be able to fix both the lower energy portion of the spectrum as well as the multiplicity width of the multiplicity distributions. We now try to talk about the dependence of the emission of gamma rays or the angular momentum as a function of the energy of the fragment. One very interesting and useful way to look at this is by looking at the plot that I've shown here on the left. This is taken from Niffenegger from 1972. This plot here shows the variation of the total gamma ray energy, that is the energy summed between the light fragment and the heavy fragment dissipated through gamma ray emission, as a function of the total kinetic energy shared between the two fragments for a certain fragment mass split. This is a lot of different restrictions and clauses, but there is a reason for all of them. Well, first of all, choosing a certain fragment mass split fixes the Q value of the fission reaction. So there is going to be a certain amount of energy that is released during the fission. This energy will be given to the fragments in two forms, either in kinetic energy or is internal excitation energy. By varying the kinetic energy on the x-axis, we are complementarily changing the internal excitation energy. So we can take the x-axis to be an inverse or a negative of the excitation energy that we would find in that fragment pair. Lastly, the fact that we have to look at total gamma ray energy rather than a single fragment emission is because gamma ray emission, as I mentioned earlier, is quite isotropic, and it's really hard to distinguish between the emission of the two fragments. They mix together very well. On the top, on the lower right plot, I show what we have for the experimental results of investigating this. So as you can see from the top plot on the left, the correlations that we would observe between the total gamma ray energy and the kinetic energy is quite linear and quite strong. If we then repeat this procedure for many different masses of the light fragment, we can observe that the slope characterizing the correlations between gamma ray energy and kinetic energy is of the order of between -0.08 and -0.1. Now, to give a quantitative meaning to this number, we can think about that for every extra 1 MeV of energy imparted to the fission fragment, about 80 to 100 keV of energy is dissipated through gamma ray emission. I should note here that, of course, there is not a experimental consensus yet on the values of this correlation slope, and that most of these results are actually taken from the 70s, so they have not been updated in a long time. However, when we look at model-based calculation, and here I only show Freya, but this would also hold true for CGMF and other fission event generators, the slope of this correlation is very small. In fact, the mechanism for the creation of angular momentum in this generator does not allow for a strong production, for a strong correlation. So now we can say, if we take this to be true, if we take these experimentally determined slopes to be correct and these correlations to be strong and positive, how do we explain that? Well, in the current model-based calculation, what we take the angular momentum production to be is simply a distribution of the angular momentum levels and increasing in the density of higher angular momentum levels with energy. This increases the angular momentum of the fragments very, very slowly, and therefore we do not expect gamma ray observables to change very much with energy. However, there have been proposed in the past, such as the plot that I show here on the left, other mechanisms for production of angular momentum in fragments, which would be more relatable to a direct torque between the two fragments at the decision point. There are several different ways to interpret this that can lead to both negative and positive correlations, depending on the energy range. Another point that we should discuss is that in the previous slide, we talked about only the total gamma ray energy emitted by both fragments at the same time. However, there is a way to reconduct this to a single fragment. In fact, we have investigated, not we, but many groups have investigated in the past, the same slope that I showed earlier of correlations of emission with kinetic energy for fixed fragment masses for neutron emission, and these are known much better. And as you can see, there are many investigations over the past 50, 60 years that have also stood the test of time. So they have been in agreement over the decades. By combining this information on this plot with the one that I showed earlier for the gamma ray correlations, we can say that given any correlation, at least one of the fragments must be as correlated or more correlated than with what we observed for both fragments at the same time. So the fact that we do observe strong correlation means that at least the light or the heavy fragment must be as correlated or even more correlated than that. Now, this is not the only evidence that we have for the presence of these strong correlations. In fact, we can also look at other indirect measurements. The one that I show here on the left is, and I'm gonna only briefly touch upon this. The one that I show here on the left is a correlation plot where the Newton multiplicity is plotted as a function of kinetic energy, again for fixed fragment masses. Of course, as I said earlier, neutrons and gammas are complementary emitted particles, so everything that's not carried away by Newton emission is taken to be carried away by gamma ray emission. By energy conservation and knowing the excitation energy of the fragments, we can subtract off all the energy emitted by neutrons for different internal excitation energies and see how much residual energy was carried away by photons. When doing this, of course, we have to take into account that neutrons do not only emit energy through their internal kinetic energy, but also through the binding energy that binds them to the nucleus. The residual energy is consistent, in fact, with a strong correlation of gamma ray emission with the energy of the fragment. The central plot here shows another type of correlation that indicates again strong correlation. In this case, instead of looking at the excitation energy of the fragments after fission, we can look at the excitation energy of the fragment before fission of the compound nucleus. In this case, we do have to look at a different system, not californium-252, but rather uranium-235. We do hope that the aspects of the fission process that apply to this system can be equally applied to a heavier isotope like californium. In this case, as we change the energy of the incident neutron, we see that the gamma ray energy, shown here as the middle of the three curves, increases quite linearly with the incident neutron energy, indicating again a strong correlation between gamma ray emission and excitation energy of the system. There are, of course, a couple of bumps and outliers there, which correspond simply to the second and third chance fission energies. The last evidence that I wanted to describe today is actually something that is going to be one of the main topics of a later presentation by Stefan Ocker today. And this shows the event-by-event correlations of neutrons with gamma rays as a function of their energies. As I said in the earlier slide, gamma rays come in two flavors approximately, where the statistical gamma rays come with high energy, low angular momentum, whereas collective gamma rays come with low energy and high angular momentum. The fact that we do observe a much more positive correlation between neutrons, which are a good measure of the excitation energy of a fragment, and collective gamma rays, shown here in the lower energy band of photon energies, indicates again a strong positive correlation between gamma ray emission and excitation energy of the fragments. So just to conclude, of course, these results are not definitive. They are based on past experimental results, and which we have compiled and reanalyzed. Yeah. But this is no substitute for a real experiment that we can perform. And therefore, one of the goals right now is to design a new experiment using both organic and inorganic scintillators, as Dr. Jovanovic actually mentioned in the previous presentation. What the goal is of this experiment will be to investigate the fragment energy dependence of this correlation for gamma rays as well as neutrons at the same time. I would like now to thank all the MTV consortium for giving us the opportunity to do this research. This would not have been possible without all the great collaborations that the MTV has provided, including the collaborations with Berkeley, Livermore, and Los Alamos, the people who are actually developing the fission event generators, as well as Lance at Los Alamos and Oak Ridge for giving us the opportunity to do the experiments, as well experiments with plutonium and uranium isotopes, which hopefully are going to be the isotopes of interest in the non-proliferation work that we're planning to do. And with that, I would like to thank again the MTV consortia and the audience here for coming together, and I'm open to any questions.
Thank you, Stefano, for this very interesting talk. Many years went into this, I know, since you've come to Michigan, so it's come a long way. Really interesting work. Thank you for your presentation. We had some interesting discussion going on the chat, I think between David and Ramona, but that was already, I think, answered.
So should I open? I'll open the chat. I don't know how to.
If you like to comment on this question, so David asked, are the angular momentum and excitation energies properties of the specific fission fragment, or can be different for different fissions? And Ramona commented on that, but I think that that's already answered. So unless you have anything to add, I'll give you a moment to read it.
So yeah, I think I'm going to excitation energy properties. I mean, if Ramona answered it, I don't know what else can I add. Maybe instead of answering something that I think that she would have given a much better answer to, I'm going to answer to something that she asked Leah earlier, which is, of course, all the research that we do, we always use two base cases. And I think the next presentation will show this method. We always do two sources in all of our MCMP runs. We do an IPOL on completely uncorrelated source as well as a FRIA correlated source. So this gives us a null hypothesis where the correlations are not included, which gives us the system response. And then in FRIA, that's what gives us the prediction of these correlations.
I actually did have another question though, if that's okay. If you don't mind, it's okay if it's going to be too hard, but could you share your screen again? Because I had a question about that angular momentum versus excitation energy plot.
Yes, I think that's the one. So like it's like 5. Yeah. Here?
Yeah, there it is. So like when I look at this plot, it kind of like makes me think that like, I mean, I apologize. I'm a nuclear engineer, sure I should know this, but I'm actually not sure if gammas from, fission products are emitted simultaneously, or if it's like this like one at a time kind of thing where it bleeds off a little bit of excitation energy and angular momentum with each gamma, or is it like all at once sort of?
None of these emission happens simultaneously. So there is kind of like an evaluation process, like it's a really sequential emission. So you start off with the fragments, there is a temperature of the fragment, well, there is an initial condition, it then emits a neutron, then it checks, am I above separation energy, then maybe I can emit another neutron, then, each particle is emitted independently. Yeah, and that's actually a very interesting question for the timing, because I think that's actually something that many people are interested in right now, is the timing of emission. So neutrons emitted super fast, no detectors that we can design for now will ever find this time difference between them. But gamma rays, actually, they can reach kind of like stable states, isomeric stable states. They can be, maybe like last 4 or 5 nanoseconds, maybe even longer than that. And this is not delayed emission. This is still prompt emission that just lasts a bit longer. So you can imagine that, especially when, if you have a very low energy, there are not many states below, so it's going to take a longer time before an emission takes place. So these last few photons might actually be happening with some delay to them. Not of the order of milliseconds, but of the order of nanoseconds.
Okay, thanks. That was a pretty good answer. Thank you.
Thanks. Ramona, did you want to unmute yourself? You had a comment to make.
Yeah, I'll make a comment to the comment. So these photons that come out, they typically tend to come out after the neutron emission for the most part, and the first ones are statistical, and then you get down. If you go back to slide 2, you see the no, it's 3. Sorry. Oh, 4. The spectrum up in the upper right. The CGMF calculation shows a lot of dense lines below, say, 1 MeV, and that's due to getting down from the statistical into the transitions between various states as it makes its way towards the ground state, and so those are very specific transitions to a given fragment, and those are happening within different time windows, and for the most part, like Stefano said, they're fairly fast. You can get hung up by a longer lived transition that will be longer than the time that it would take for the detector to recognize it. So then your cascade stops before getting towards the very end. But that would maybe come out as a delayed photon instead.
Okay. Yeah.
So does that help too?
Yeah, no, I just found this really interesting, this whole like timing thing as well with the photons, especially at the lower energies. So I just wanted to like ask about it because it seems like something that could be potentially very useful. So.
Yeah, I mean, it all happens very, very fast. I mean, neutron emission is on the strong interaction time scale, so a few femtoseconds after the fragment, and then the photon emission is electromagnetic, right? So it comes later, generally, and in time, and then the statistical ones come out before before these transitional ones.
Yeah.
Okay.
And if I can add one like super last very fast thing with that for David, it is very interesting, these correlations also, and as you said, for applications, we do have actually some research that was done a few years ago where you take the time difference between 2 gamma rays, and you would expect it to be the time resolution of the detector, like if you had sodium, but instead we do see some breadth to that distribution, and that's because in fact they're not emitted all at the same time. So that's actually something that Evan Leptink, I think, did in the past, and we're starting right now again to explore again. So
okay, cool, thanks.
Great, thank you for that interesting discussion. We are right on the time.